Thanks. So it was funny, I went on Twitter a couple weeks ago, and I was like, I hear all the time in the InfoSec industry, oh, I worked on my slides the night before. And I thought, that's very disrespectful to the audience, to the organizers. You should really practice. You should really practice a lot. So I worked on my slides for a couple weeks, and then I reserved this week for kind of practicing the talk. And then I got the flu. So ironically, this is a relatively unpracticed talk, despite my lamentations on Twitter. So I'm going to talk about deserialization. I got into this space last year when Gabriel Lawrence and Chris Frohoff released exploits against practically every piece of Java software on the planet. And I was shocked because every exploit I saw was this like beautiful piece of art. And so now we need to get past the stage where it's not ooh and ah anymore. It's not scalable to have only really premier security researchers like Matthias Kaiser, guys who are like JVM super experts, be the ones to be able to find and exploit deserialization flaws. So today my point is I will be dropping a few new attacks, new exploits, but the point is to, my point in my research was to find a really repeatable process where you can find code entry points, discover gadgets and chain them towards exploitation. The examples today are all Java specific, but the techniques aren't. And so all the exploits today have been disclosed, but only some of them have been fixed. So let's get started. So of course, everybody knows little Bobby Tables. But the point here is deserialization is really just another data becoming code problem. The issue is that deserialization exploits are just not very visible. SQL injection is very intuitive. You jump out of a data context into a code context and all within a single string. It's just very easy to understand. So the execution of malicious code in a deserialization attack has nothing to do with the format of the message or what the message looks like. So you can look at the attack and learn very little about how it's going to work. This is also a reason that's very difficult to signature for from a perimeter kind of standpoint. So this really doesn't have too much to do with my talk today, except to say that the path from vector to exploitation is pretty muddy. And I think that's kind of stunting our tribal maturity on the subject. So let's get into it. So what is deserialization? So serialization is the process of taking an object within an application, breaking it up into bits, and communicating those bits, usually over a network, to another application or back to yourself. And the receiving application then reconstitutes those bits back into an object using the reverse process called deserialization. So think Star Trek teleporters. Most modern serializers use JSON or XML, but the very high performance ones and the ones that are usually built into your language are binary. So one thing I want to make clear is that when we're going to go through the talk, when I say I want you to deserialize an object, you're really deserializing an object graph. Most real-world objects have a complex model. So this is going to come in handy for us. So these are some of the popular deserialization libraries, and they're going to be our targets today. So we're going to assess these deserializers using my framework and find out the best ways to attack them. So really, my framework is just kind of a series of questions. You could look at it that way. And those questions focus your review of how the deserializer works to just the security relevant bits. So the main question that we should start with for every deserialization library is what code does the deserializer call on the objects that I send you? So we're really talking about grouping the answer to that question is how can I group the different types of side effects I can have on an application in the deserialization process? So I control the data in the objects I'm sending, and as part of the deserialization process, you end up calling code on those objects, and this is how exploitation always starts. When I first looked at the exploits from those researchers I mentioned earlier, it was impossible for me to understand. Embarrassingly, it took me an embarrassingly long time to figure out how they work. But they always start with the deserialization process calling some code. So what code can you get the application to call? Sometimes there's code in a type that's used to override how deserialization should occur. There can be side effects from that. When you're reconstituting an object, you need to create a new instance of it. This in itself can have side effects. Sometimes the deserializer code just calls code directly on the objects as part of the process during reassembly, usually after objects have been instantiated. And we're going to go through each of these. And then finally, when an object is reclaimed via garbage collection, there's sometimes you can create side effects from that. So let's talk about the first one, custom deserialization methods. So some deserializers, and this is how really Java's works, let you control how objects get deserialized. So there's a default protocol that's pretty safe, but it's possible that for your custom object, you can figure out a really space-efficient, time-efficient way of deserializing that. So you can override the behavior. So if you override the behavior, you won't go through the safe protocol, and you'll go through your own custom read object call. So, of course, developers don't think, when they're making this type of behaviors, that it could be maliciously repurposed for some other means. And so there's going to be side effects. So it's when that custom read object is repurposed towards malicious means that a lot of these exploits that I talked about already have already been disclosed, how they start. So this is an interesting type provided by Spring. So the purpose of the object is really irrelevant. It's some type of really deep in the bowels of Spring. But if I ask you to deserialize this type, Java will call this read object for us. And what this does is it takes a class and a method name supplied by the person who's sending the message, and then it calls that class and method name. So clearly developers weren't thinking about, the opportunity for this to be repurposed maliciously. So this is, like I said, this read object type of side effect is the one that's been most popular for all the exploits that we've seen. So this is the second category I talked about. So this is Cryo. This is how Cryo works. Cryo is a binary serialization library. It's very, it's one of the cool kids. Used at the big forward-thinking dev shops. So when Cryo's reading an object and discovers the type that it's supposed to be reconstituting, it just creates a new version of that, new instance of that class using the constructor. So I give you the class, and then you call its constructor. So of course there's going to be side effects there too. So some constructors, I'm sure, have permanent, maybe dangerous side effects. So here's an example of that, and it's from Cold Fusion, which under the hood is really just Java. So the constructor for this type calls a static method and registers the new instance of it as kind of a singleton to be used statically throughout the application. So what's interesting here is, this is a private method, so we've kind of bypassed the security, the developer's intent. Right, the developer's intent was that this not be instantiated by anybody but me, but the deserialization library is kind of thrown that away. So by using Cryo, we can now replace the shared resource that was in use before and deny service or otherwise behave maliciously. And so we've scaled our attack kind of outside of the deserialization process and cause side effects. So the upshot of this particular exploit was to return unexpected nulls all over the place and just take down the system in really one packet. So I registered a static variable that had null for every value, and so places that were previously getting valid objects were getting nulls and nullity references everywhere, and it just blows up. So how do you instantiate an object safely? So Cryo, we saw called its constructor, but that appeared to have side effects. So how are you supposed to do it safely? There's different ways, and they all have their different security pros and cons. So we're going to look at the choices that these three libraries made and see how that affects the security. So Java's deserialization library, when it wants to create a class, it actually calls its superclass constructor, the first non-serializable superclass constructor, and really just it means there's almost, you can instantiate almost any object, right? It has to be marked with a serializable tag, but it's a lot of types. So this is bad news it's good news for people who use the library, right? Because they can deserialize and serialize a lot of different types, but it's good news for attackers because you can deserialize a lot of different types. So I have a bigger pool of gadgets to choose from. So when I call this the immediate gadget pool, we're going to figure out a way to expand our gadget pool to include other types, but the immediate gadget pool here is pretty big. Because it's not explicitly invoking constructors, though, there's less direct side effects from Java. So cryo, as we saw, calls the constructor. So it limits the immediate size of the gadget pool a little bit because you can only instantiate objects that have zero argument constructors. But it has the benefit to the attacker that you can use those constructors to cause side effects. So Xstream is our last option here. This is an XML serialization library, and it uses like even darker magic than Java to instantiate objects. And it's really good because you absolutely cannot cause side effects. So that's great. But the bad news is the attacker's gadget pool is almost limitless because you can instantiate all types, not just serializable, not just those with 0R constructors. Anything's fair game. So if we see there's really no right answer here, there's always a trade-off. So what I call, again, I spoke a little bit about the immediate gadget pool. So this is the set of classes that you can trick your victim into deserializing. So we're going to talk about ways to expand the pool later. So again, just to recap, Java, you can only deserialize classes that have serializable interface, cryo, any class with a 0R constructor, and Xstream, any type, even sun-misc unsafe. So this is like the holy grail of Java hacking, this sun-misc unsafe class. So it can be used to play with direct memory and do all kinds of super illegal, dangerous things. I'm not suggesting that you can do anything. Just me being able to instantiate this object in your system, even if I can't call any methods on it or do anything with it, is a serious trust boundary violation, in my opinion. Okay, so now I'm just going to talk about methods that are just incidentally called on applications as part of the deserialization process. So we talked about instantiation, constructors. So now I want to talk about this example with an Xstream. So, one of the CVEs the only CVE that got fixed actually was for a product called Jenkins, which a lot of people I think probably know and use. So it's a popular continuous integration software. So my exploit started with that type of method. So Xstream handles maps in a certain way. So if I want you to deserialize a map, this is the XML that I send you. So the first thing in the entry is the key, and the second thing is the value. So maps are always, there's a key, and then when you fetch that key, you get the value out. So in our case, these are both strings. So this is this pseudo-ish code of how Xstream works underneath the hood. And so when it's reading entries, for every entry, it reads the key, and then it reads the value, and then it calls map.put with the key and the value. So I control both of those objects. I can supply any arbitrary object for those two things. So we dig into that hashmap.put method, and we can see that the key we control actually has a method called on it. Okay, so this is the entry point. This is the code entry point. This is the beginning of the chain of exploitation. So all I need to do now is figure out some way to make some type's hashcode method do something evil. And this is a little tricky because hashcode is a very simple method. It's just supposed to return an integer. So what are the likelihoods we can figure out a way to turn that into remote command execution? Seems very slim. So I have to choose a type that's available within Jenkins too. So there's lots of different types out there in the world, but if they're not packaged within Jenkins, I won't be able to invoke them. So I looked at all the libraries in Jenkins, and I found Groovy had an answer for me. So Groovy gave me a type that's called an expando. So an expando just allows me to delegate the hash code call to anywhere that I choose. So you can see here, I've started the chain. So I had a hash code call that led to an expando hash code call that I can now chain to another method. So skipping some of the gory details of how that worked, there were 6 or 7 things in the ellipse, I think. But this is really where the art and the creativity of the exploit authors really shines through. So it's a really fun adventure, and it's part of the reason why I have such respect for those exploit authors, because they find really creative ways to get from A to B. So I found another method where it's closure call, another type where the closure call could lead me to another gadget, until it finally gets to the point where I can have a remote command execution. So no matter the type of the 4 side effect types, so instantiation, side effects during this, during reclamation, etc., the concept of chaining is always the same. At first, I figured out how to get a hash code invocation done on my object. And I kept paving new roads for myself, figuring out new ways to call other code. So I went from hash code to closure call to foo, to another place, and eventually I got to process builder start. So that was the CVE. So this is what the final exploit looked like. I set up a handler for the hash code method, delegate to a method closure, which wraps another thing, blah, blah, blah. It's not worth talking about. I think there's a whole write-up on it if you want to look into it. And it's been fixed for some months. But you can see what I was talking about before. When you look at the exploit, it's much more difficult to understand than a SQL injection exploit. It's not clear how this is going to end up getting executed. And that's why I think we're having a little trouble with this subject as a community. Okay, so let's talk about the last way deserializers call code in your objects. And this is during reclamation or garbage collection. So for Java and Cryo, when you create an object, you're calling either a superclasses constructor or, in the case of Cryo, the object's constructor itself. And what we see is when an object is finalized, meaning when an object is ready to be reclaimed by the JVM to reallocate the heap memory, you can actually set up a callback in your code by overriding a method called finalize. So you make a method called finalize, and then Java will call that for you, right? So this is there's a really interesting point in a talk given by Alvaro Muñez and Christian Schneider, I probably butchered those names, where they found out that if, what's an interesting point about using finalize is that any security manager that's run during deserialization doesn't matter, because finalize is called by another thread in a whole another context where there's essentially no security manager. So anyway, here's an example of abusing a finalize method. So, not something we typically see in an AppSec world, is memory corruption, right? Memory corruption leads to remote code execution with a talented enough exploit author, which I am not in that space. But if you can cause arbitrary writes to memory or arbitrary writing operations, I'll say, you can cause a lot of havoc and usually lead to remote command execution. So this is a type that comes with Sun. So I can trick you into deserializing this type, right? And I control this long address. So this is a memory address. And so when finalize gets called on it, which the garbage collector calls, it eventually delegates to this native.free call. So this is like your standard library, malloc free method. So this is, this is going to be just like C, right? This is going to try to call like a C free call on any memory address that I control. And so this is another exploit where I found where you could just blow up any JVM you wanted by simply sending it a message, right? I trick you into deserializing this type. Clearly, the implicit contract between the developer who's using this library and the library authors isn't that if I use your library, people can one-shot terminate my JVM. But that's not the case, right? This kind of visibility into what people who are deserializing messages can be victim to is totally invisible to the users of those libraries. So this is an example of, I realize that's very small, but that's a native kind of OS error saying pointer being freed was not allocated, and it just blows up. So somebody like Dave Itel could turn that into a nice little exploit. So what can we use this for? Well, there's a ton of gadgets out there. So this memory class is what we call a gadget, right? So there's a ton of gadgets out there that will delete files for you, overwrite files, do memory corruption, and file descriptor hijacking. So a lot of people, a file descriptor is just an integer. And so if I can trick your file descriptors into doing different things, that's really interesting. So I've actually, in kind of a lab setting, I've been able to trick a server into writing its logs to the same file descriptor that is the socket that it's communicating with me. So I can actually get you to send me your logs, which is interesting. So of course there's, in every different deserialization library that you look at, it's going to have a different set of useful and available gadgets. So how do you find the types with which to build your exploit chain? This is a really painful process, it was for me. So I was just trying to use my IDE and grep code and just kind of very manually brute forcing this. And I know I wasn't covering that much of the search space. So we made a product called Jugal. So it's a simple static analysis tool used for finding immediate attack gadgets as well as chaining gadgets. So if you wanted to say find any, like for my exploit, right? I needed to find types that provided a hash code method. Well, I could, use Jugal to find it. So I used Jugal to scan, my cached Maven repository of thousands and thousands of libraries. So I ran it on that, and I said, give me all the classes that implement hash code. And I could I could add other attributes, and I could programmatically make the search space even more interesting to me. So I could say, give me it if it's got a zero argument constructor and it has a static side effect, right? And this is static analysis, so it's fairly limited. It doesn't understand type trees or, if there's a subclass that has that implemented, but the super type doesn't, it won't know that. But this has been very good for our own exploit development. So I kind of glossed over so far, how do I get you to deserialize my type, right? Like you'd think, well, when you deserialize something from someone, shouldn't you be, controlling what types you're getting? And the APIs are a little backwards in that regard. So if you look at the example from Java here, so this is how you deserialize an object from Java. So if you know much about Java, you can see that we called a read object, and then we casted it to the Acme message. The Acme message is what we wanted, but we deserialized the type first, and then we checked if it's what we wanted. So this is a little screwed up. If it's not that, then it'll throw a class cast exception and it'll error, but it's too late. The attacker's already tricked you into deserializing their type, and that process is what leads to exploitation. So Xstream has the same flawed design. So it's easy for the attacker to choose, what types you're deserializing. So this is the only one who you can't do this with was cryo. So this presented a different kind of challenge. So when you want to read an object with cryo, you say, I want an Acme message. Deserialize what's coming in as an Acme message. So we had to get around this. So we had to create something called type stuffing. Okay. So this is one of the test cases that I have online. All these, all my research is in the form of test cases that you go and see on GitHub. So what I wanted to do was figure out a way to trick a cryo receiver into deserializing one of my types, not one of their types. So you can see here that I created a list of strings, and I added 3 strings to the list: contrast, security, and foo. So then I used some reflection
and I dug into the objects themselves, and I overwrote them. So, I'm kind of bypassing here the compiler time checking by by doing this at runtime here. So I went into the array that's underneath of an array list, and I changed it so that it's got 2 strings, but then it has a long value. So now the internals have a long instead of a string. So then I wrote that out using cryo. So now I have this like tainted cryo. So now I have some other code here where I read in that cryo again. So I take a rebuilt list. There we go. And I read object on the output that I sent. Does that make sense? So I made the hacked stuff, and then I read that hacked stuff as if I was, a real victim reading that in, and then we checked what was in it. And so even though I told cryo that it's supposed to be an array list of strings, when I read it in, you can see with my assert equals here, I realize this is a little code heavy, but the first thing was the first string I stuffed in, the second thing was the second string I stuffed in, and the third thing was not a string. It was a long that I'd put in. So even though cryo tells me it's going to deserialize, only an ACME message, if there's any type of collection or array or almost any kind of complex object, I'm still able to provide an unexpected type because it's really a compile time check. Now, if you ever tried to use any of these things as strings, then the JVM will throw an error and say that's not legal. But because all I need you to do is do the deserialization process, that doesn't matter. I don't care if you throw away my objects as soon as you see them. It's the deserialization process that I need you to complete and nothing else. In fact, throwing them away is how we made some of these attacks work, right? Like the finalize attack actually wouldn't work if you didn't throw it away, because then the reclamation methods would never get invoked. So really the framework comes down to enumerate the code entry points, right? So I talked about those 4 different places where a deserializer would call code on your objects. A custom deserialization methods, object instantiation, in-process method calls, and object reclamation. So those are your 4 entry points. So if you wanted to go find the next great deserialization vulnerability, now you know how to assess them. Because you look at all the places in the deserialization library where it calls code on those objects. So enumerate the media gadget pool, right? What types does deserializer allow me to make right off the bat? And then what types can I stuff in to places that are unexpected? So then really the next part is the part that's hard to automate, and it's hard to have a playbook for, but we provided some static analysis tools for you today to do that. So iterating on the gadget chain extension, how can you get a hash code to behave maliciously? How can you get innocent code to get to be used maliciously? So the big trick in the community so far has been to use scripting languages. So Groovy and Scala and Jython, a lot of these packages are available. Their main purpose is to turn strings or files into code, right, that runs on the JVM. So having them on your class path gives opportunity to attackers to use those classes to be repurposed to be carrying out arbitrary code execution on their behalf. I'm not saying don't use those things. I'm just saying those things made some of my exploits possible, made a lot of exploitation possible for the exploit authors. So object deserialization is really dangerous. You shouldn't do it. But it's not all bad. I mean, there are ways forward. So JSON and XML are preferable formats, but just having XML doesn't protect you, as we saw with Xstream. It's really more about the library that you're operating on. So this is just a little simple rubric, and this is one of a bunch that I have on some of my blogs on this subject. So this is JSON is Google's JSON library, and you can see that it's really not super dangerous to use. The attacker can't control the root type. The attacker can't stuff arbitrary types into collections. It doesn't call constructors. So the amount of side effects you can produce are almost none. It still doesn't try to constrain references. It doesn't handle back references very well. So, I mean, it's easy to perform DOS attacks against libraries like this. But at least you can't get people to allow remote code execution. So not every library turns up like garbage when you look at it closely. So there's lots of open source solutions, and my talk is really not about solutions today. It's really about finding exploits. But there's plenty of stuff for you to use. There's lots of great code out there to help. There's libraries that help you harden how you use deserialization. And there's my preferred approach, because I'm an agent vendor. So agents are the best way, I think, to solve this problem, because even if you change your code to be secure, that doesn't help you if your app server or your library is doing the deserialization. So in all the exploits released last year, many of them were against WebSphere and JBoss and Jetty and I don't know what else, application servers. So you obviously can't go into their code and change it to be safer. But with an agent, you can modify the code as it's being loaded to introduce security in those points. So these are three different agents that you can turn them all on today and be a lot safer. And they're all open source. So really what I want you to take away is that a deserializer's weakness, it can really be modeled and analyzed in a repeatable way. There's some parts of it that can still be art in the gadget chaining, but the rest of it you could do just by really just reading the code. And I've given you the tips, I think, to find the places to look. Some of the decisions that deserialization libraries should make are really security decisions. I mean, they think they're design decisions, but they have huge impacts on security. So we released a tool to help you find gadgets. And so it really for the Java folks in the room, stick to Jackson and JSON. Those are the safe options. And really that's it for today for me. Thanks.
Questions?
Really interesting talk. Thank you. My question is, what was the nature of the fix for the vulnerability in Jenkins? Was it to blacklist or whitelist what can be put in a map, or was it something else?
Yeah, it's a great question. So what did Jenkins do to fix it? So they did exactly that. They just enforced some type control. You can configure all of these libraries to be safe, to only deserialize expected types. But of course, nobody does that. So that was their fix. And Cryo, actually, I finally got a ticket opened I opened a ticket a long time ago, but they finally acknowledged it. And they're in a real pickle because they have to choose whether to make a backwards incompatible change to prevent attacks like this. And so I don't think they're going to end up on the side of security, which is maybe not surprising. But enforcing type control is the way you fix it, and it's never the default.
This may be the exact same answer that you just gave, but with another dangerous thing, XML parsing, some parsers are starting to have like a secure mode or a constrained mode that people can opt into if they know to do that. Are you seeing that become a thing that serialization libraries either offer or will offer, or is that not applicable?
They all have the option. Really, everything I've looked at's had the option, except in the case of JSON, where the contract is concrete all the way down, and there's no need for a control like that. They have it. It's just most people choose not to use it.
Any thought on that? People don't know how to use it, or don't know to use it, or the docs are bad. Anything on that?
They have no idea, right? I think they just have no idea that there's this implicit agreement to be totally hackable if I use the deserialization library. And for me, that's a bit irresponsible. And some of the Cryo committers are on my side of the argument, but it'll be interesting to see how it plays out.
Anyone else?
All right, guys, remember to put your feedback in the basket at the back as you leave. Thanks.
Thanks, guys.